Okay, so the BC calculus does vector particle motion, two-dimensional vector motion, whereas the first semester calculus does linear motion where it's just back and forth on a line. With what you're working with now, it's essentially like doing two functions at once. And if you grab a hold of that, it takes care of the majority of your questions on how this works. But there's then the issue of going up a dimension in what we're working with, because now we have two-dimensional motion, not one-dimensional motion. So you are going to have, first of all, notation. When a vector is written, we put a half arrow above it, or we write it in bold print. A lot of textbooks will just use bold print instead of putting the half arrow above it. And what it's letting you know is that this isn't your basic function. This is actually a set of functions. We have a function with respect to time for the horizontal motion and a function with respect to time for the vertical motion. And we are looking at both horizontal and vertical, creating a graph as time progresses forward. Now, the old function we are used to working with is s with respect to t. And I'm going to now move down to my comparison notes. And I didn't get a chance to erase what I had for first period because, anyway. When we were doing linear motion, it was often just called S of t, although sometimes the AP test would say x of t for a horizontally, for a function that goes back and forth along the x-axis. When we drew a graph for position, we created a time axis as a physical dimension. Because if I were to take the time dimension out and try to draw what this is explaining, then over here, let me redraw that. It might be a function that represents motion on a vertical line. So if it's dealing with motion on a vertical line, then we have a zero position and an understood positive side and negative side. So based on this graph right here, I'm starting on the positive side, and then I am heading up, and then I'm heading down to the negative side. The actual motion is I start here, I go up, I go down. And that's difficult to read if I don't warp the spatial understanding by bringing in a time axis. And it's very, very important that you understand with the vector motion problems that we're going to use, we don't have a time axis. And not having a time axis allows us to move all over the place and not be stuck in the old vertical line test situation. However, we need to understand as time moves forward, where does this graph go? So we often draw arrows on our graph to help express that that is the direction of going forward in time. And I have right here an initial point and a final point. I'll just put P naught and P terminal. And I want you to just take a good look at the issue of not having a time axis. And all you want is for this to as time progresses, be drawing only one graph, and then it's a function. Isn't that amazing? Love it. Now, you're probably curious, can I get my calculator to do that? Yes, maybe? Do you have your calculator with you? You can have your graph change to parametric mode. Vector functions are parametric functions. The only difference between them is really more a notational issue. There is no difference between them. So if you go to, on your calculator, you have a mode button. So you have a second key. If you have a TI-84, you have your second button, and then you have your mode button. If you push your mode button, can you see where it's blinking function? If you change your mode to parametric, you will see some interesting differences. So change your mode to parametric if you have your calculator. If you don't, you can just see what I've got. And I think if I push that and enter, it will work. I'm trying to. Now, if I go over to my Y1 button, I see something different. If you now push your variable button, do you see the variable button that is xt theta n? It will now put t's when you push it. And to create one graph, you have to type in two functions. So the sub one, x and y, you have to have something written into both your x sub 1 and your x sub 2. And I do not remember what I had in here or why I had that in there. But what I need to do is, there we go. Okay. So I have to have, you might notice that my equal signs are highlighted for the sub 1, x and y. If I try to unhighlight, it'll unhighlight both. Now, when you just dropped my phone on, or my calculator on my computer, that's okay, we're all good. If you go to your window button, you now have a T-min and a T-max. And if you are not graphing the whole function, if you don't have enough domain in your T-min to T-max, you won't know it unless you go over to your window and notice what the domain of T is, because T is not an axis you're going to see. So it's very important to remember that if your T minimum, typically it starts off with T minimum being 0, that will often draw only half of a graph. And you want to be aware of that. So I don't remember what I've got in here or what it's going to draw, but I'm just going to push graph and see. Ooh, pretty. Okay, sorry, let me go back because I've got to show it to you. It's really pretty, but I think it's still graphing because I put too much domain in it. Okay, there we go. I need to change my window. Okay. Now it's going to graph way too quickly. Are you ready? I'm going to push the graph button. I just drew part of the graph, but not the whole graph. If I go to my window settings and I make my T-min be -10, so I'm going -10 to +10, I'm going to see more of the graph. So here we go. Whoa. Guess what that graph is? And what did that graph look like? What would be a name for what you saw? Do you think you know what that was? It looks like a sideways parabola, but does it fully look like a parabola, or maybe one of its neighbors, shall we say? It's half a hyperbola. Mm-hmm. The first graph was a quarter of a hyperbola. And, the big difference is just an issue of having asymptotes. So you can, if you graph far enough out, you can see that it's asymptoting. Question from Jackie.
So I was wondering, when you pressed enter to like graph it, what were the x and y functions?
I don't know if you can you see? I'm just going to put them up where can you see them right now? No? Okay. I got to be careful in time. The x function is e to the t plus e to the negative t. The y function is the same but a subtraction, e to the t minus e to the negative t. Okay, so I wanted you to see the calculator, because if you start playing with your calculator, you're going to learn things about these graphs just by playing around with it. But your homework is going to be asking you to not use a calculator. Now, so as far as the difference between the 1 dimension and the 2 dimensions, I now need to go back to the beginning. Oh, that's right. I had a little GIF ready that I'll show you in a second. All right. If you have a position vector function, R, and R is typically used for the position vector in the entire calculus sequence, whereas S is used for the position function for the AB version of particle motion. Literally, if you want the velocity vector, you just take the individual derivatives of each component function and you've got a velocity vector. For the acceleration vector, you take the second derivative of each individual component function and you have your acceleration vector. So I was saying that really you're doing two functions at once when you go to vector valued functions. And that means that when you integrate, you have to consider that you are actually integrating two functions. So when you get your plus c, it's not the same plus c between the two functions. Your x component function gets its own unknown constant, and your y component function integrates to get its own unknown constant. And this is just, again, an explanation written twice of something you already know. I'm using alpha and beta, however. I'm using alpha and beta to emphasize that we are not dealing with the x's A to B or even the y's C to D. So typically in calculus, if it's horizontal and we want to write the limits, we typically use the letters A and B for general formulas. And if it's vertical, we typically use the letters C and D for the vertical limits if we are looking at that. But we're not using the X or the Y points where we are using time points. I have an alpha time and a beta time, and they are not based on the X or the Y position. So I want to really emphasize that. But all it is you have to do 2 integrals instead of 1. Woohoo! Yeah. So you know your position at a particular time. Now, what this problem is basically saying is at time alpha, your position vector is x at time alpha, comma, y at time alpha. And typically, you're just going to be given numbers. These are just numbers, but they're based on a particular time. If you want to know your position at time beta, based off of your position at time alpha, for the x coordinate of position, you will look at your location at time alpha and then add to that the displacement, the horizontal displacement. And that's what this integral is it is your horizontal displacement from time alpha to time beta. And then the y is essentially the same thing. You have a position, a vertical position at time alpha, and you add the vertical displacement from time alpha to time beta, and that gives you your y coordinate at time beta. Now, before I go any further, I want to show you the GIF I had planned because I want to make sure that you understand what is meant by vector motion. And I found this to be a nice visual. Okay, it won't shrink for me, but good enough. This is the origin right here. And if you look at something as a parametric function, you're taking a point and following a floating point. When you talk about it as a vector function, you're following the tip of the vector who is tracing out a floating point. So parametric and vector really are the same thing. It's just when you go into the physics applications of calculus, physics uses vectors. And all it is going from an initial point to a terminal point. And it does not have to move left to right. This could have been moving right from the right to the left. And it's moving forward in time has no necessary direction that you're going to automatically see. I could draw for you a graph. I'm just going to draw. Whee! Okay. Now, if you just see this and you're told that that is the graph of a vector valued function and you know nothing else, you don't know enough information. Then it could be negative. Just trying to read what you have. Okay, yeah, there's a lot you're saying in there. And let me just say this. If you just look at this and you know that that represents a vector valued function, you need to know what direction it's going. This is not enough information. This could start here and move over to here, but just as well it could start here and go over to here. So there has to be enough information in the graph. That's where either arrows help out or just saying that this is the initial position and this is the terminal position. That enough is explanation of how the time fits into it. Sometimes people will put just the time value next to points. There are a variety of ways that people will write down to help interpret how time is brought in to this curve. But again, it's not an actual dimension you can see, so the information has to be given on the plane. Now, I'm going to actually come back over here to, I'm debating because I'm thinking I may want to wait to talk about certain things until tomorrow because I lessened the homework that I was originally going to give. But I want to point this out, and I think this is really important. When you're dealing with velocity and you're working with the AB version of linear motion back and forth on a line, positive velocity meant you were moving in the positive direction of that line. Negative velocity meant you were moving in the negative direction of that line. But now we have two dimensions. We have two dimensions of motion. So this should be pretty clear once you read it. dx dt being positive or negative tells you whether you're moving right or left. dy dt being positive or negative tells you whether you're moving up or down. At rest, before just meant any time when the velocity is equal to 0. But now to be at rest, you cannot be moving in either of the two directions. They have to be 0 for the same time in order to be considered at rest. And now I'm going to move off of this. And I think what I should do is examples. Hold on a second. I need to erase. But I'm going to start you off on some examples before I explain any further. Where's my eraser? There you are, eraser. Okay, that's enough erased. Okay, here's example 1. You have no calculator. A particle moves in the xy plane so that at any time t, the position of the particle is given by, and we have our x function and our y function. You're going to find the velocity vector at time 1 and the acceleration vector at time 2. Stay ahead of me, see if you can get this problem started. Perhaps I should warn you that some of your homework problems today are trying to force you to remember how to take derivatives of functions that people typically mess up on. So know that part of the homework is trying to force you to remember derivative formulas. But for the example, we're just going to keep it simple because of time. So we take the derivative, and I'm just going to go into the second derivative because it's easier to keep going than to come back. And then for the y, first derivative, and then the second derivative. Now, the velocity vector at time t is the vector valued function of, and I'm just trying to say a little bit more than what the problem is asking for. We have our x component of velocity and our y component of velocity. And if I want to know my velocity vector at time 1, I'm just going to plug a 1 in, and that's going to give me 11 and 1. Then for my acceleration vector as a vector valued function has a first component function, comma, a second component function. And I just realized I probably didn't mention this. Vectors are normally presented as pointy brackets that look like little triangle or angle things. Pointy brackets tell you you're dealing with a vector, and you put a comma in between the two functions involved. And if there are more higher dimensions, you just keep comma, next dimension, and you can keep going. Then if I want to know my acceleration at time 2, and if my pen works, okay, let's not do this again. Over the weekend, I had a really hard time with my pen and had to restart my computer, and I hope it is not doing that to me again. There we go. Thank you. Don't have time to restart the computer right now. So my acceleration at time 2 is whatever I get when I plug 2 into those t values. And to avoid arithmetizing incorrectly by accident, I'm going to throw the answer up. I trusted myself with plugging 1 into t's, but not fully with 2. Oh, good question. Why didn't they put an arrow on top? They should have. They should have. Is because if it's properly written, it either has a half arrow above it or it's written in bold print. Also, most calculus textbooks don't present vector motion in the way that BC Calculus presents it. So a lot of teachers have adapted to creating, basically not using the textbook when it comes to the vector valued functions. They typically introduce vector valued functions in 3-dimensional calculus. And so it's all presented in 3 dimensions, and it's kind of, well, tricky. Okay, now, for those of you who have had physics, vectors are composed of two things. What are the two things that make a vector? Oh yeah, there you go. Magnitude and direction. This example is asking you to find the magnitude of the velocity vector, so just its length. And I'm going to talk to you a little bit about what that is. But first, I want you to find the velocity vector at time 1. So just like the previous example, we're going to find velocity at time 1, but there's going to be an extra step. And you might figure it out before I get there. I'm trying to erase what I had earlier before I hit it. Whatever. You guys are differentiating away. Derive. But don't drink and derive. Ha ha. Actually, it's don't drink and derive, but it's not quite funny when it's pronounced incorrectly. Okay. My velocity vector, 2t plus 3, 3t squared minus 6t. My velocity vector at time 1. Now what that's saying is if I look at just the velocity vector as a vector, vectors are typically drawn where the initial point is at the origin, and then these give you your final location. So 5, -3, I'm going to approxiplot it there. Often when a velocity vector is drawn, it is drawn on the position graph to show I'm located here and I'm moving in this particular direction. However, that does not change the magnitude or the direction of this vector. If I were to actually look at the location at time 1, I could put my initial point at the actual position x of 1 comma y of 1, and then draw the vector from there 5 units right, 3 units down. But you're just being asked to find the magnitude of this vector, so we don't need to go that far. All we need to do to find the length of this vector is pull out what theorem? Pythagorean theorem. So if you want to find the magnitude of your velocity vector, you find your velocity vector, and then you Pythagorean theorem it with those being the two legs. (25 plus 9, 34). Now, in the context of particle motion, what is the square root of 34 telling you about the particle's motion? And I'm trying to see if some of you with a physics background know where this is going. Yep, it is speed. The magnitude of your velocity vector is speed. And now I'm going to compare speed. And whoops, going the wrong way. This was the way I intended to go. I want to compare our speed formulas between our linear motion and our new two-dimensional motion. When we were dealing with linear motion, we had a function with respect to time, and we might have looked at the graph of the velocity with respect to time. The speed was just the absolute value of velocity, which would basically just be how far the velocity is from zero. You're just taking the absolute value. If you're dealing with one-dimensional movement, distance is absolute value in the way that you're used to thinking of absolute value. But two-dimensional distance is also sometimes called absolute value because absolute value is actually just a distance from zero. Your speed is your velocity vector's distance from zero. It is the magnitude of your velocity vector. We have 10 minutes left. And I also want to point out to you that when we did distance traveled, we had to integrate speed to find out the actual distance traveled. Now, before, that just meant absolute value of the velocity function and integrate, because all we were doing was taking anything that had a negative velocity, reflecting it up, and integrate that. Yay! But if you want to know your distance traveled in two dimensions, you are still integrating speed. In fact, anytime you want distance, speed is who you're integrating. And later on, I'm going to explain to you, but not today, that this is the same formula for arc length as a parametric function's arc length, because time is not one of the physical dimensions. Over here, the arc length formula for a function is very different from this formula you see here. And I just want to throw that out there, and then I'm going to talk about it again. Come on. There we go. And then let me point out to you the difference between distance traveled and displacement in our two-dimensional system. Distance traveled is the arc length from your initial point to your terminal point. Displacement is just looking from at a straight line shot from initial to terminal. That is my position vector. Or I should say, that is my displacement vector. And if I want to know let me come down over here. Oh, no, it wasn't there. Sorry. Forgetting where I put things. If I want to know the magnitude of my displacement, I actually need to make sure that I know first what is my horizontal displacement and what is my vertical displacement. If I integrate my, shall we say, velocity, my horizontal velocity from time alpha to time beta, that will give me my horizontal displacement. If I integrate the y component of velocity from time alpha to time beta, that will give me my vertical displacement. But then to find the actual magnitude of my displacement, I have to Pythagorean theorem those two. So I wrote this down as more of a process because it is not easy to write that all shoved into one formula. When it comes to the particle motion we're used to with the one dimensions, we have our formula for total distance traveled versus displacement. Pretty similar formulas. But anytime you go up a dimension, you increase the complexity of the math that needs to come in dramatically. And I think it's really, really important to help you to see the things that are the same and the things that are different when it comes to particle motion. You will still be testing on AB's particle motion, but you will now have additionally vector motion. And I've got to tell you that what I have here as a list are the key things you need to know about vector about vector motion problems. It's all you really need to know for the AP exam. And usually I can get through this in a day, but I talk about this for an hour and a half, not an hour. So I want to talk about this a little bit more tomorrow and make sure that it's clear and do some more examples with you. So today's homework is going to be much more straightforward problems like you saw with the examples. And again, a lot of it is practicing, can you still take a derivative? Because you know you need to practice it. Annotated version. Is this the annotated version? I can do that. Yeah, I'll do that for you. So understand with your homework, there are two things I need you to do, and I'm going to have them both posted on Google Classroom. One is a normal homework assignment that's worth 4 points. The other one is the quiz that I'm trying to send you to. Part of it is to try and get you on Go Formative, and part of it is to review material at the same time. I've got to tell you that on this Monday, I feel very hectic looking at trying to squish an hour and a half into an hour. And that's all I have to say about the fact that we're having to do that in every math class. It's horrendous. Are you guys having the same thing with your other academics? I should stop